Okay, let's talk about electric potential, potential difference, and the electron volt. We might not get to the electron volt today, but we'll definitely get to potential. Come on now. All right. Electric potential. And what we don't say is energy usually. Just say electric potential. So, we're going to start this with a diagram. So we're going to start by looking at a Van de Graaff machine. I think it's a good illustration. It helps me, I think, understand a little bit about this, this topic. So a Van de Graaff machine is like this. Okay. Let's draw myself a little Van de Graaff machine. And inside here, you're going to have a little roller. Down here, you can have a little roller. These are going to be dissimilar materials. Usually it's like felt and amber, or amber and felt. I think depending whether you want a positive or a negative charge up on this guy. And between there is a dielectric band. Basically a rubber band, a big fat rubber band. And what ends up happening is this gets spun in a circle. Okay. There's a metal cone here. Actually, I don't want that. That's going to be in my way. So there's a metal comb inside here, which is like a little copper piece of wire with a bunch of little like whiskers sticking off of it. And then that will be connected to the metal sphere. So this is inside the metal sphere. Okay. This is also a dielectric or an insulator. Okay. So in other words, this metal ball is insulated from the ground, right, up high to sort of prevent arcing to the ground. And this will be spun around, and there's another comb at the bottom. Okay, get that in. And this is connected off to a ground. Okay, so this gets spun, right? This conveyor belt gets spun. And essentially what goes on is electrons, due to the dissimilar materials here, are built up on here, right? And they have a path to ground, so they just leap this small little gap over to ground. They push off, okay? So this thing comes down, and what that does is it sends this up to the ball with a positive charge, right? So positive charge rides up the conveyor belt, okay? When this positive charge gets near the little comb, electrons get pulled off of the metal ball onto here, right? And they ride back down, and they're pulled off down there. So in other words, you get this conveyor belt moving charges around, or separating charges, okay? And something that you will notice is these two bands will attract together. If this is too loose, these bands will like suck together and you'll get terrible charge. So when your Van de Graaff starts to wear out, this rubber band gets loose, these just attract together, right? And that makes sense. The two dissimilar sides attract together and they share their charge back, okay? If everything's working correctly, you will begin to build a large positive charge all around here because you're basically pulling the electrons out of there, okay? Something else you'll notice is that as this charge starts to build, you'll hear the motor of the Van de Graaff machine get louder, right? It's working harder, okay? Why do you think the Van de Graaff works harder as charge builds up? Exactly right. So there's positive charge on the ball, and you're trying to like push more positive charge towards it. Of course, there's a repulsion here, and what that means is in order to get charge up into here, you have to work, okay? So work is done in this direction. Work, if you remember, is a force applied over a distance. So in this case, the distance is the distance of this rubber band, right? The force is how much push the motor has to put on this thing, okay? And therefore what that means is the potential energy is created in this ball. Now, that's maybe not exactly clear, but let's make it clearer. Let's just take this example right here, okay? If we have a positive field, we have a field, okay? In general, it doesn't have to be positive, sorry, I shouldn't have said positive. If we have a field, and we take a positive charge and we move it from here to here, we would have to do work, okay? If we release this charge, it springs back to where it was, or even farther away, right? So we say, much like if we were moving up in a gravitational field, right? If we move a mass up in a G field, we say it has more gravitational potential energy, right? So there's your force, mg, times distance, but we call it height. It's up above the Earth. Now you're doing kind of the same thing, but with charge, right? And it's a little more interesting, I think, because you could actually move negative charge away and do work there too, right? So now let's imagine you have these two places in a field, and you insulate one from the other so that charge cannot pass directly to a point of, we'll say, lower potential, right? So an area of higher potential and an area of lower potential. But you maybe attach a conductive wire, force it through a filament in, like, say, like a light bulb. Let me see here if I can draw a nice light bulb. Not really, but okay. And as that charge, if you have some charge stored there, right? Like we have like a big Coulomb worth of electrons or something like that, they'll pass back through here, coil through this, and move over there. Okay, so what we're saying here is that you can actually create a current of electricity if you have a reservoir of charge in one place that's at a higher potential than another place, and that Coulomb of electricity can pass through there. Okay, so this is kind of a general concept. We're going to use this. The work here is done by the spinning of the motor, okay, which is electric usually in a Van de Graaff nowadays, but it could be crank powered just as well. It doesn't really have to be electric. It's just a matter of being able to spin this and move it up here. So now you can imagine, right, you have all this positive charge on here. And if you're cramming a bunch of positive charge together, the impetus is for that charge to be pushed away from there, right? Now, we're going to kind of bring in some electron concepts here, because we know that it's electrons that move. If you talk to like an electrical engineer or a classical electrician, they talk about positive charge moving to negative. Reality, it's the electrons that are moving. But let's say we attach this to ground, right? It turns out that our Van de Graaff that we have at this school can build 20 kilovolts, okay? 20 kilovolts of potential. So, the question is, okay, so kilovolts, great. What does that have to do with anything? So, our first definition here to kind of get this sorted is that 1 volt is when 1 joule per coulomb, sorry. 1 joule per coulomb. So in other words, if we have a 1 volt potential here, right, what it means is that if a coulomb of electricity passes through here, it will do 1 joule worth of work. Or, in order to move 1 coulomb of electricity from here to here, it requires 1 joule. Okay? Does that make sense? So is a joule a lot of work or a little bit of work? It's not much. Okay? It's not a whole lot of work, really, 1 joule. It's like lifting 1 kilogram 10 centimeters. That's 1 joule worth of work. Okay? It's not a ton. So if we say 20 kilovolts, that means every coulomb of charge we can get on here can do 20,000 joules worth of work. So just, again, 20 kilovolts means every coulomb of charge you get up on here, and by the way, you're not going to get anywhere near a coulomb on here, but if you did, right, well, if you did, right, you'd have 20 kilovolts, or you'd have 20,000 joules worth of work up here, which is significant, okay? You might be able to get, like, I'm going to say a microcoulomb on here, maybe a microcoulomb, maybe a little more, 100 microcoulombs or something like that. So not a huge amount of, or not a huge amount of charge, but high potential charge. So the charge that is there has lots of potential. So how do I view potential? Personally, I think of like a can of those like spring snakes. And if you cram them into a can, they want to like spring out. You take the lid off, they'll like spring out. The more you pack them in and the tighter you pack them, the more they want to spring. So it's almost like pressure. you could think of this almost like a pressurized tank of air or something like that, right? And you're jamming more and more in, and therefore the pressure to push charge out is greater and greater and greater as time goes by. Eventually, if I don't hook a ground up to this thing, there's enough potential that the charge can just push off into the air, and you can bring your finger just close, and it will actually arc over, so it'll ionize the air, and it'll push charge. I keep saying push charge off, but technically what's happening is electrons are rushing into it, but it's sort of irrelevant, okay? So now let's imagine, right, we've got a bunch of charge on here, and we put that to ground, and we put our light bulb on here. So let's just fix this up. Okay, so what's going to happen here is if we put and now we're going to bring in the concept of a resistor. If we put something that resists flow in here, right, the current, which we're going to talk about in a second, will push through here. But really what we're saying is that electrons are getting pulled up from the ground. The ground is literally the ground. It's the Earth itself, okay, or something with, you know, very large, with lots of electrons on it that's not going to miss them. These electrons get pulled up. As they travel through here, okay, they do work. And you can think of it with a light bulb anyway, a lot like friction, okay? They're essentially rubbing along inside this filament, creating heat, and they're creating enough heat that it's going to start to glow, okay? So now what we're saying is creating a potential over here allows the electrons to do work somewhere else, okay? And we're connecting it by a wire. So basically what we've made here is like a circuit, okay? So electrons come in, they pass into the ball. As long as we leave this running, if this is a certain type of bulb, it's not going to work really for an incandescent. But if you put like a fluorescent tube here, you would see glowing and sparking, and it would turn on and off, right? Okay, and as these charges pass through. This is a very inefficient way to make current electricity, and it's not done this way. But this is just sort of bridging the gap between having a collection of charge and then getting to the point where we can now somehow use it, okay? This is a direct current, right? Charge would only ever be able to go this way in this system. But if now instead of a Van de Graaff, you replace it with a battery provides both a voltage and a supply of current. So we have like a 1.5 volt battery, okay? You can make like a little flashlight glow in the exact flashlight battery glow in the exact same sort of way that we were just talking about, okay? Or 3 volt or whatever it happens to be, okay? You're still going to get this drive of current through here. Now, let's forget about electrons completely. Let's talk about what we would actually say is happening. So for physics, this is positive and this is negative. We just say current travels this way, okay? So what is current? That's the next question. Before I answer that, I'm going to introduce an interesting analogy, and that is just the analogy of water towers, okay? That's electricians, electrical engineers, really anyone who designs circuits, for the most part, talks about it this way, positive to negative. We don't believe anything. This is the way we're going to do physics and problems. Positive charges move to negatives, okay? And again, that goes back to the whole Ben Franklin silk glass rod thing where he guessed which one was positive. He just sort of guessed backwards. Really, in practical terms, it doesn't really matter all that much. You know, unless I guess you're dealing with things like diodes and so on where current can only travel one way. But even so, with a diode, you say it travels from positive to negative, but not negative to positive. So really what's happening inside the diode is sort of the opposite of what you would say. It's not positive to negative, it's negative charges traveling in the opposite direction. But it, again, does not matter, right? Sort of irrelevant. So let's imagine this is a water tower, okay? And to get water into the water tower, we have to lift it up. So we would need some sort of like pump to take water from like a pool, which is down here. Okay, and it's going to do work to lift the water up a pipe and into this reservoir. Okay, so now this has potential energy. In this scenario, it's this, right? And we could actually say, right, we can measure the amount of water in terms of liters, couldn't we? Okay, so we had another water tower that was the exact same height, but was much larger. okay, let's just think about the different properties this would have. It would simply have more liters of water, right? But the potential would be the same, right? The potential of each liter is the same, okay? So let's say the height of this is such that we get 1 joule per liter of water, okay? Well, this is also 1 joule per liter of water. Which one can do more work overall? The big one can do more work overall just because there's more liters in it, right? So there's more total joules in it, okay? This is a lot like 2 different types of battery that have the same voltage. So you know we have like your little AAA battery, A. It has 1.5 volts. So every coulomb of charge within this battery can do 1.5 joules worth of work. Or you can get a big D battery. It's also 1.5 volts, right? It's just that there's a lot more of it, okay? So what we're saying is, much like with this, we have a pump, it's a chemical pump in a battery. It's refilling our reservoir. Well, I should be careful here. Don't worry about the pump, sorry. The fresh battery is like a full reservoir that's already been pumped. Maybe that's a better way to think about it, okay? So now, what we can do is we can put a pipe here, okay? And this pipe resists the flow of current, or the flow of water coming out of it, right? It's a thin pipe. You can't, like, if you just like cut the bottom out of this, it would all like fall out in like a split second. Extremely high current, right? Like a short circuit actually, okay? So we have the exact same pipe. Would you expect the flows from these pipes to be the same? Yeah, I think so, right? Okay, so the flow out of here, we could measure in terms of liters coming out of here every second, right? So we're measuring water in liters, and we're talking about 2 different properties of the water. How much work it can do per liter, and then how fast essentially it's coming out, or what current it's going to flow out at, okay? We can do the exact same thing with a battery. So we say it has 1.5 volts or 1.5 joules per coulomb. We can also measure the current coming out, okay? And we measure the current in what units do you think? Amps, which are actually the what? So if we measure water in liters, how do we measure charge? Coulombs per second. So an amp is 1 coulomb per second. This is my made up thing. It's called a Johnson. Okay, it's the liter per second of water flowing out of here. All right. And each of these has, you know, 1 Greg worth of potential in it. Okay. So 1 joule per liter, whereas this has 1 volt. All right. So this is basically the 2 sort of fundamental ways that we talk about electricity. And the last piece to the puzzle, right, is how much current we're going to get. And it's sort of a function of both of those concepts, right? If we have, you know, some voltage and we have some current flowing, what we could do is we could actually shut this off. So we could turn off the tap. Let's say we put a big, huge, fat pipe on here, right? And it's short. Well, the resistance is less, the current will be higher for the same amount of voltage. Or what we could do, okay, is we could actually raise the water up higher, have it run down the pipe and out. And in that case, right, if the water's higher, there's more of a column of water above the pipe and it's going to rush out at a higher current. Sure, and let's talk about that. Okay, let's say we take a really high water tower like this. Now let's say we have a low water tower like this. Okay. And let's say this one is, you know, 10 Gs. Call that 10 Gregs, which is, again, 10 joules per liter. Okay. And this one is 2. This one is 2 joules per liter. Okay. And I connect them together. You would. 8 joules per liter worth of work can be done from here to here. So you could technically, although I would not recommend this, take something like a 9-volt battery and you could hook it up to a 1.5 volt battery and you could do, what, 7.5 joules worth of work across here. Of course, ramming charge into a battery this way is very bad for it, so don't do this, okay? But technically you could think that. Now you might say, so what is this in relation to? And that's a very good point, right? Potential is a relative thing, right? So we call this the ground in this state, okay? Now where this breaks down a little bit is there's a problem, right? We're using gravity as an analogy, and gravity can only work in one direction, whereas charge can work in both directions. So you can actually have positive and negative potential, right? You know, don't overthink that at this point. Really just, this is, I think, the best way to talk about this. And then, right, of course, this could further flow down towards the ground. Okay, now let's imagine that you do have this current starting to flow in here. You can make it do work for you, right? You could hook up like water wheels to this, and you could have these water wheels spin, and you could hook them up with, you know, belts and whatnot, right? And really, this is how a lot of work was done in, say, like flour mills, or even in electricity generation, but whatever, okay? But as this water is flowing down, you could actually extract the work from it, right? Extract the potential energy from it to do work, is what I should say. Okay, so you could get this to, like, you know, hook it up to a machine that lifts things, or you could hook it up to a machine that spins around and gives you high fives all day, or whatever you want, right? But you can harness the potential energy of this raised water, right, to do work. So you can also harness the potential of these raised coulombs, like this, to do work. Okay, does that make sense? So let's just recap what we've learned here. We've learned this. I, which is current, okay, is the charge passing a point in a given amount of time. I equals Q over T, or the way I always remember it is just this: Q equals I T. Quit. It's easy to remember. Q equals I T. And the units here are coulombs passing a point every second. So the unit is coulomb per second, which we call the amp. It's a special name named after Ampere, okay? Then we also have the voltage, right, or the potential, or as we call it often, the PD, potential difference. Okay, so the potential difference is electric potential energy. Okay, so E sub E, electric potential energy, which is the energy, big E, there's lots of E's involved here. This is the energy E, okay, which is energy per amount of charge, okay? Which actually, this has its own special symbol, so we never actually see it as EE, electric potential, like that, which we also say for elastic potential. You just got to make sure you know what you're talking about. Voltage, right, is equal to potential per amount of coulombs. Okay, so the units here, of course, are joules, coulombs, or joules per coulomb, like that, which is called a volt. So amps and volts, that's what they are. Okay, they're related like this. Okay, so this is resistance. Essentially, it's the ratio of voltage to current. Okay, so if I have my water tower up here, right? Okay, and I have two pipes on it, just as a recap. One's a very slender little pipe, okay? So it's gonna have, like, you know, its flow, and then one's like a big, huge pipe here, okay? It's gonna have a larger flow. This is sort of a little bit weird, because really what we should be talking about is down at the ground where this pipe is, and actually let's just make that a little clearer, because this is sort of important, its flow at the bottom of the pipe, because otherwise it won't make sense. So let's just redraw that quickly. So we have a pipe, a little skinny pipe that looks like this, okay? Or we have a big fat pipe that looks like this, okay? So for this amount of potential, okay, we have this amount of flow, right? larger flow, lower flow, okay? Right, so if we have this at given voltage and we have a large current, we have a low resistance, okay? Low resistance. If we have this much voltage and we have a little bit of current, we have a large resistance. If I take the same pipes, but I make the water tower much higher, okay, both currents will go up, okay, with respect to that, okay. Right, so now we have a much farther way to go here. So we have a larger column of water standing on top, so we have much higher potential here, okay. The current will be larger, the flow will be larger, okay, but they'll stay in proportion to each other. So the resistance would remain the same, right? It's just that now you have a larger flow because you have more potential pushing the water through that amount of resistance. Does that make sense? Okay, so in electricity, right, this is just volts per current. So volts per amp. So the volt per amp has a name as well. And it's called the ohm. And the ohm is just a symbol. Looks like a little horseshoe, but it's an omega. Okay? So here's your little challenge. What is ohms in MKS? So in base units. How would we figure that out? Well, let's have a look. So R equals volts. What was volts again? Joules per coulomb. Good. And what was amps? Coulombs per second. So we could say this, right? R should be equal to joules. Coulombs, -2. Seconds, -1, right? Does that make sense? Oh, sorry. There we go. My bad. And what was a joule again? I did it for you. Force times distance, right? So it's, yeah, so it's Newton meters. Okay, and what's a Newton again? Okay, so then break that all down and what do you get? Meters squared. Seconds per second, sorry. And per coulomb squared. I think that's right. Does that look right to you? I hope that's right. I think it's right. But it's easier to just say ohms, right? So there it is. There's electricity in a nutshell.